Hello, this is Jim Corkins, and we are continuing on with projectile motion. This is the second part of this video. Okay, now I broke it into three sections because the problems that you do at first don't kind of look the same, but they really are the same, and they're getting a little long in this series. So I want to break it up, that way you have a little bit of time. You don't have to spend 2 hours watching one video. Okay, so let's move on. Let's go ahead and try this problem, okay, where a ball is launched at an angle and lands at the same height. Now, again, with projectile motion, always the acceleration is going to be pointing down at 9.8 meters per second squared, so long as we're in a free fall situation. The weird part, again, about projectile motion is the velocity will be constant in the x direction, as we learned in the last problem. But in the y direction, it could be speeding up or slowing down, or even not moving for an instance. Okay, so here's what I mean by this. So we're going to launch a ball up and to the right. Jake is going to throw a ball to me. And so this ball is thrown up and to the right. That means as it's rising up to its maximum height, which is going to be right here, and if this is launched at 0 seconds, 1 second, 2 seconds, 3 seconds, so it reaches its maximum height, and then it's coming back down at 4 seconds, 5 seconds, and 6 seconds. So it'll be in the air for a total of 6 seconds. But as it's moving up to its maximum height, you can see that, again, in the x direction, its velocity is going to be constant, but in the y direction, it's going to be slowing down. And then when it hits its maximum height, it's going to come to a stop in the y direction, but it will have a velocity in the x direction. Once it reaches that maximum height, it's going to turn around, and its velocity in the y direction is going to turn around 180 degrees and begin speeding up as it's moving down, all while continuing to move at a constant velocity in the x direction. Okay? There's some weird uniformities. And what you could see here is that if it's launched and caught, and its total time in the air is 6 seconds, it's going to reach its maximum height at half the time of flight. Okay, so that's really weird. And at that half time of flight, it's going to have a velocity in the x direction, but no velocity in the y direction, because when a ball reaches its maximum height, its velocity in the y direction has to be 0, although it will have a velocity in the x direction since it's moving in 2 dimensions. What the other thing is if you look at the size of that green vector here and the size of this other green vector, they are the same size. When you throw a ball up in the air, the velocity that you shoot it with is the same velocity it's coming down with. Just like when you throw a ball straight up, it's going to be coming back down with the same speed that you threw it up at, just like we learned before. So those similarities are going to maintain in projectile motion. Okay? Let's move on. So here are the basic rules that we just discussed. Again, we have done this before. We've done this in our tutorials when we did 3.1, just motion in 2 dimensions. Okay, so in that tutorial we had to draw our vectors. It moved from here from 1 to 2 seconds, 2 to 3 seconds, 3 to 4 seconds, 4 to 5 seconds, and then it wasn't moving in the y direction, and then 6 to 7 seconds, 7 to 8 seconds, 8 to 9 seconds, and 9 to 10 seconds. So we're going to do this because it's going to help us learn projectile motion in two dimensions. Okay, so let's break up those vectors. Okay, in the y direction, it looks like it's moving up 1, 2, 3, 4. So that's going to be positive 4 meters per second. But in the x direction, it's moving over 2. So it'll be positive 2 meters per second. So that's its initial velocity, or what is launched at. All right. Now, let's do that again. It's moving up 3, so that's positive 3 meters per second. And again, it's moving over positive 2 meters per second. Okay. Now, when it gets to 3 to 4 seconds, is moving up positive 2 meters per second and over 2 meters per second. We're running out of room. So let's try this again. I'm going to write this positive 2 over here. I'm going to zoom in too as well. And then this is going to be over positive 2 meters per second. And then we're going up positive 1 meter per second. And then over 2 meters per second. At this instant, it comes to a stop. So now all of its velocity is just in the x direction. So its velocity in the y direction is 0. While it does have a velocity in the x direction. And then we continue on with this whole part. And I'm just going to hurry this up. So this is going to be positive 2, positive 2, positive 2. Yep. And positive 2. In the y direction, you're going to have negative 1, negative 2, negative 3, and negative 4 meters per second. So you could see the velocity was launched at in the x and y direction is the same velocities that same speeds it's coming down with. Okay, so let's take a look at these specific parts right here. And I think these little times are off. I'm sorry. This should say 1 second to 2 seconds. And 2 seconds to 3 seconds, and we're going to comparing those to 8 to 9 seconds and 9 to 10 seconds. And again, the acceleration is going to be an instant between the first, basically happening at the 2 second mark. Okay, and this will be the instant that it's happening at the 9 second mark, and this should say 2 seconds to 3 seconds, and this should say 9 seconds to 10 seconds. Okay. All right, so here we go. So in the x and y direction, in the x direction, it's got a constant velocity in the x direction. Positive 2 meters per second, positive 2 meters per second, and positive 2 meters per second. In the y direction, it's moving up at this speed and then it changes to positive 3 meters per second. From 8 to 9 seconds is moving down at the same speed in the opposite directions. And what you could see is the interchange between the 2 to 3 second mark. You can see that the velocity in the x direction is 0 meters per second, and the interchange between the 8 to 9 second and the 9 to 10 second, there is no change in velocity of those two parts. Now, its acceleration in the y direction looks like it's decreasing by 1 in the y direction from at the 2 to 3 second at the 2 second interchange to 3 seconds, and then from 8 to 9 seconds compared to 9 to 10 seconds. So at that 9 second interchange, it looks like it's still -1 meters per second. So again, the overall average acceleration, and those should be squared, should square those, is going to be overall 1 meters per second squared, which is like saying 9.8 meters per second the entire time. So you can see again that this is 2 halves of that one motion that we saw where you shoot a ball off a cliff and it falls down, right? And then it's falling down at this speed. But from a certain point of view, you could say that if you throw a ball up here and it lands right here, you take those 2 halves and put them together and you have this. So they are really the same problem. The unknowns and the knowns that you have are really interesting. So you know that if you throw a ball and it gets caught at the same height, here's a couple things that we know based off of these rules right here, okay, is that since it's being shot and caught at the same height, its change in the y displacement is 0, right? If it starts at a height of 0 and ends at a height of 0, its delta y is 0. If it's being shot up at that angle, whatever it's being shot up at in the y direction, which is going to be a positive right here, that'll be the same speed that it's coming down with. Okay, positive 4 meters per second, negative 4 meters per second. So positive 4 meters per second, negative 4 meters per second. So you know the speeds are the same in the y direction. You also know, like always, that the acceleration in the y direction is -9.8 meters per second squared. In the x direction, you do know it's got a constant velocity in the x direction. Okay. The only thing that you have to do at the beginning is they're likely to tell you just what the initial velocity is. So in this case, let's see if we could actually figure out what this black velocity is right here. Okay, and how we figure that out is we do c squared equals a squared plus b squared. So the x direction is going to be positive 2 that we're going to square. Plus the y squared part, which is going to be positive 4. So we know the overall launching speed is going to be this, right? So whatever that is, let's take a look at what that is. So that's 16 plus 4, that's going to be 20, so the square root of 20, is that 4.64? Nope, I was close, 4.47. 4.47 meters per second. Okay, And the angle that it gets launched at is theta right there. So that angle is going to be the inverse tangent of opposite over adjacent, which is going to be 2 meters per second over 4 meters per second. Which is the square, it's, what is that, a half? So 0.5, trigonometry, here we go, inverse tangent, 26.57. So 26.57, yep. So most likely what's going to happen is they are going to just tell you it gets launched initially at a speed of 4.47 meters per second at an angle of 26.57. And they'll ask you questions based off of that. So you will have to do trigonometry to figure out those components, which we actually already know, 4.47 cosine of 26.57. Well, that is going to just be the x direction. That is going to be positive 2. Right? So that's just positive 2 meters per second. And then this one is going to be 4.47 sine of 26.57. So that initial velocity in the y direction, which we started with, is this. So when they give you a problem that he is launched and caught with, the first thing you have to do is figure out what these x direction speeds are. Which it's got a constant velocity the whole time. And since this is the initial velocity in the y direction, you actually already know that the final velocity in the y direction is just the negative value of that. Right? And then you know, since it's getting launched and caught at the same height, that is 0. That change in delta y is 0. It will have a change in the x direction, of course. And you also know the acceleration in the y direction is negative 9.8. So let's apply what we learned from this. Okay? So, this is a good problem to practice with. Okay? So, at a shot put event, an athlete throws a ball with an initial speed of 12 meters per second at an angle of 40 degrees. And they want to know how far the shot travels and what height it reaches. Okay? So there's some nuances to this. So again, write your equations here. All 4 of your equations, that should be a sub y. Write the 5 variables associated with the y direction stuff. In the x direction, write your 3 variables and your x direction equation. Again, look at the values. This is 12 meters per second at an angle of 40 degrees. And they're saying it's hitting the ground at the same height. Well, first thing we should do is we're going to put question marks next to what we're being asked to solve for. Okay? Now we know we're going to have to solve for everything, including these question marks, but let's start off figuring out a few things. Since this is being launched at 12 meters per second, we at an angle of 40 degrees, let's go ahead and figure out its starting velocities in the x and y direction. So in the x direction, which will be its final velocity in the x direction, because that's a constant velocity, let's go ahead and figure that out. So that's going to be 12 meters per second cosine of 40 degrees. And that'll be to the right. Again, if you don't know what direction they're talking about, make it to the right. It just makes it easier. So this is going to be 40, and it is going to be cosine times 12 equals 9.19. So that's its starting velocity in the x direction and its final velocity in the x direction, 9.19 meters per second. So I'm going to fill that in right here. Now its starting velocity in the y direction is going to be equal to the 12 meters per second sine of 40 degrees. So let's do that again. So 40, we're going to do our sine, and then we're going to multiply that by 12. So that's 7.71. So you know it was launched up at 7.71 meters per second. Okay, now we're going to fill that in. But we're going to apply what we learned from right here. Okay, now what we've found out, if it gets launched at that angle, it does have a constant velocity in the x direction, so we know it's going to have that speed in the x direction the whole time. We also know the velocity in the y direction, initial velocity in y direction that it gets launched up with is the same speed it's coming down with, but just downwards. So we're going to fill that out. And we also know the acceleration is going to be this. So we actually have a lot of information. We also know when it reaches its maximum height, so I think its maximum height, that's going to occur when its time is equal to, so this distance right here, the maximum height, that occurs half the time of flight. The time it takes to get up here is the same time it takes to fall down there. So the time of flight, if we determine that total time, which will be this time, if we divide it by 2, that will tell us the maximum height it got to. Okay? All right. Now for right now, the way we've set this up, it's change in height. If it was going up and coming back down at that speed, we also know its change of height in this case is 0. We're not going to use this to figure out what the maximum height it gets to. Okay, we need to figure out the time it takes to go from here to here, and that will be what we're going to be finding first in the y direction, which will tell us the time in the x direction, which will give us delta x. Then we might have to change a few things. To get the delta y, this occurs at the time of flight divided by 2. And we know this, that at that, whenever an object reaches its maximum height, one of its definitions of maximum height is a velocity is equal to 0 in the y direction. It's going to have a velocity in the x direction, but we know in the y direction it's going to be equal to 0. Okay. So there's a lot of ways to solve this second part. But let's figure out the time in this first part. Now, any one of these equations that has t in it we could use, since we have the other 4 variables. So let's use my favorite equation. V final y equals V initial y. Let's do it in the format that it's shown. That is a sub y delta t. That's supposed to be a sub y, plus the initial velocity in the y direction. When we do our algebra, we end up getting this. We've done that a whole bunch at this point. So for the total time of flight, It's coming down with the same speed that it was sent up at in the y direction. And we're going to be subtracting that positive 7.71 meters per second, which is the initial velocity from it. Okay, and we're going to divide that by the negative 9.8 meters per second squared. So the delta time there, I suppose I could just take 7.71 negative and multiply it by 2, but I can't. 7.71 negative. Let's try that again. 7.71 negative minus 7.71 equals, and we're going to divide it by 9.8 negative equals 1.57. So 1.57 seconds. Luckily, that didn't work out to be negative. If you get a negative time, you've probably made a mistake in the directions of your velocity vectors or your acceleration vector, right? Or you figured out time travel. If that's the case, please email me how you did it. All right, moving right along. So now we know that the time it takes to go with that total time of flight is 1.57 seconds, which means this is 1.57 seconds, which means we could get what delta x is. Delta x is going to be equal to the constant velocity in the x direction times time, which is going to be 9.19 meters per second as positive, it's to the right, times 1.57 seconds. So the delta x is going to be equal to a positive 9.19 equals 14.46. So it travels 14.46 meters to the right. Okay? So we know how far it traveled in the x direction. Now to get the velocity, to get the height in the y direction. To do that, we're going to have to write our variables again. And we only need the y direction variables since and the acceleration right there. Let's figure out what we know. We are actually solving for the height in the y direction. Now we know it was launched up at 7.71 meters per second upwards. We know again from this tutorial that when it reaches its maximum height in the y direction, that is going to be 0. That is velocity in the y direction is going to be 0. So we know its velocity in the y direction at that maximum height is going to be 0. We also know the acceleration, even though it's not moving at that maximum height, that is its acceleration there. We also know that this occurs at 1.57 seconds divided by 2, which is, we know the time it takes to get to that maximum height. So that's going to be 1.57 divided by 2, 0.785 seconds. So the time it takes to get up there is 0.785 seconds. Now we have a lot to work with. Okay, we just need to have a delta y to work with. This top equation right here is really, I don't like it. I just don't like it. I like this one because it can be really easy in this case. So that's the one I'm going to choose. I could have chosen this one, or this one. Just can't choose this one because it doesn't have a delta y in it. So I'm going to write that third equation out. V initial y plus V final y delta t. And so the delta y is going to be equal to 1/2 the initial velocity in the y direction, which was positive 7.71 meters per second, plus 0 meters per second times 0.785 seconds. And we're going to divide all of that by 2 for the 1/2. So let's figure this out. 7.71 meters per second plus 0 is just 7.71 meters per second. We're going to divide that by 2. So now that's the very first part of this. Now we're going to multiply that by 0.785 equals 3.03. So we know it reaches its maximum height at 3.03 meters. And since we're on the ground, it's going to go above us 3.03 meters. Okay? This is a really good problem to practice with. And a lot of your homework problems are like that. Okay? A lot of them are asking for what height it gets to, how far it travels in the x direction. There's a lot of good problems. This one problem actually encompassed this problem right here and this problem right here. In fact, this problem here is the same problem as this one. It's just a football. Excuse me. So this is the second video in projectile motion. I hope you liked it. Have a good day.